My name is Josip. I come from a company called SofaScore, and this talk is about scaling from 0 to 20 million users. We actually have a bit more than that, and I'm going to tell you a story on what issues we faced, how we solved them, and maybe you can take home some of the mistakes we made so you don't do them, and also some infrastructural things we did that you can maybe apply to your own business. So the app itself is complex. It's actually an app to follow live sport results and statistics, and we have heat maps and all sorts of graphs, which is not important for this talk, just to give you an idea what the app is. We have the application and we also have the website. In terms of numbers, we are currently at 23 plus million monthly active users, which generate around 800 terabytes of data, of traffic, outbound traffic each month, and that's across 250 billion requests. So it's not a simple application. We do have a lot of interesting problems to solve. As far as technologies go, we have a lot of different technologies. The usual for mobile development, and as far as backend goes, it's mostly written in PHP, as Facebook was one day, so you can do it in PHP also, and we have a little bit of Go and Node.js and some Python. We do care a lot about the user experience on the application in the sense that we want it to be fast and stable. So the users really get the best possible experience, and that shows. We have quite a high mark on the Google App Store and Play Store. So when we started, we didn't actually know anything. So if you were at the awesome keynote from Dom, I always felt the imposter syndrome because we had to solve problems. We were straight out of college. So we didn't actually know how to solve them. We were just stumbling across to get to where we are now. And this was our growth. So once we solved an issue and number of users grew, we had whole different issues to solve, and that kept repeating year after year. So we started, it wasn't a garage, but it was a small desk in an apartment we rented. So we kind of, you can see how grainy the image is, how old it is. The way we started is like most projects, you just have one server, and that one server does all of it, which is like the default, and especially was the default in 2010 when we started. So the database and the backend were on the same server. And then like when a couple of users come online, they crash our server because there aren't enough resources left on the server to kind of serve all of the users. So what we ended up doing was just hoping that some of them will go away. So the really persistent ones can view the results. Of course, this wasn't really something you want to do as a business. And in part, the reason why it was crashing is because of the technologies that we used in that time. We actually weren't managing our own servers. It was a company doing that for us. And then they didn't really know how to do it well. They literally installed VHM and cPanel and just clicked through to get the PHP installed, which is not something you should do in a production server, especially if the app is, having traction. But it kind of worked. So we didn't know how to really fix it. And they said, well, you just take two servers and that will fix stuff. So you just separate the backend and the database, which is something that one does. And it did help a little bit. The good thing about this setup is you should always separate your services to different servers, especially if the load is getting bigger. The good thing is you can really see how much your database is using and how much your backend is using. And the thing about PHP is it uses really a little memory, a little RAM. So what we did, we had the opportunity to install Memcache to kind of cache the content. And that helped a lot. So that's when we figured, okay, we have to invest into using that cache more because it really helps with the system. But you get the cache stampede problem, and that's when something expires from the cache, it's no longer in the cache, you get all of these different users going after the same thing. And since it's not in the cache, it goes to the backend, but all of the requests are the same. So you get a problem where you actually recalculate the same thing over and over again before you save it to the cache, before it can be served from the cache, which is not ideal. And what happens is your database dies, or your backend, or wherever. So ideally, what you would want to have is just one request. And this is called request coalescing. And it's not the simplest thing to do, depending on what software you're using. So if we go back to our setup that we had at that time, where we have the memcache, which actually stores the full page cache, the HTML of the website. So we kind of took a look at how our users are using the application, which is important. You have to know how your users are using the application in order to better optimize your setup. So what we found out is that mostly, as it would make sense, people watch live games. They don't watch games that are old, that are 1 year old. So they watch games that have passed in the 1 hour or that will start in 1 or 2 hours. So what we did was actually create a worker that would proactively fill the cache in the memcache. And that's called proactive caching. And it helped a lot because all of the important content, all of the high impact stuff was already in cache. So we kind of got around the cache stampede effect. And that's something that we no longer use, but at that point, it was the best we could do. So we have a really interesting thing. So there are some really big matches that happen all around the world. And in those matches, like 15 minutes before, we have a certain number of users. As those 15 minutes pass for the game to start, the number of users doubles, even triples sometimes. So the load goes really high, really fast. So there was this game called El Clasico. It's the match between two of the most popular football teams in the world. And what happened is the server, 15 minutes before, the server started getting really high load. The CPU was off the charts, and you only have 15 minutes before the game starts. So we were kind of thinking, what can we do in 15 minutes? Keep in mind, this wasn't cloud, so this was a dedicated machine. You cannot buy another machine, plug it in, and install everything in 15 minutes. So you have to get creative. So what we did was kind of think, what can we do to kind of allow our users to follow this match? It's really important. And we got to thinking and remembered that Apache is much, much faster in serving static content than PHP is in calculating the dynamic content. So we got to thinking, so what if we could serve this particular match as a static content from Apache? So we did file. We went on the game, file, save as, and saved it as HTML. And then we uploaded it to the server via FTP because that was the technology we used back in the day. And we wrote a simple Apache rule to, like, if you go to this specific match, which is the most important one, just load the HTML from the disk. And it worked. And the load fell down. And everything was great, except it wasn't live, right? You cannot have both. So what we ended up doing was just watching the game live and then manually editing the HTML file and uploading that file to the FTP server. And it worked. Yeah, so that's how you scale. Thank you very much. So. I'm kidding. But like sometimes you have to get creative and hacky to solve the issues right now and then use that to think about how you could improve your system over time. So at that time, cloud was all the rage. Actually, it wasn't all the rage. It was just starting. I think this was 2012. And I was explaining to the owners of the company, like, this is the ideal thing to do. We should move to the cloud because most of the time our load is low, but at certain points in time, we have a really, really high load. So 10x increase in load in a very short amount of time. And they said yes. And they asked me, do you know how to do it? And I said, of course I do. I did not know how to do it. So Amazon was the only choice at that time. And we said, yes, okay, we're going to go with Amazon. And I got a lot of confidence from them that I can do it any way I want. So I started researching on what we could do. I wanted to utilize that principle we use to solve that one big match to have the content cached, but in a much simpler way. So I stumbled upon Varnish. If you haven't heard it, it's basically a reverse proxy that sits between your users and the backend, and it caches all the content. This is the single most critical piece of software that we have that enables us to really scale to the number of users that we have. So one of the things it also does is request coalescing. So if something is not in your cache and you get 1 million users trying to get that same thing, it will only pass one request to the backend. When that request is done, it will cache it and then return 1 million requests back to all of the users. So your backend services are really getting almost no impact if you do your cache properly. So this is how the infra looked. It was quite simple. So we had an auto-scaling group that ran an image. That image contained both the Varnish and the backend servers, and then we had some more instances that were doing background tasks and jobs and whatnot. And this is the first screenshot I could find of Google Real-Time. They call it real-time, even though it's not real-time. It's in the span of 30 minutes. But it's the number of users that are on your site at any given moment. So those were kind of records that we were breaking in 2012. And those were cause for celebration. And since we didn't know any better, we wanted to try out every new technology that we could think of without properly researching if it's the right fit for us. So in 2013, MongoDB was all the rage because, web scale. So we said we have to use MongoDB. Why? Because we have to. And we did. And you get a nice replication. And you get certain benefits that were useful for us at that time. And it was interesting technology to use. Also, at that time, we added queues. This could be a whole talk for itself. I'm not going to go into much details, but if you do not use queues, you should. For any product that is going to grow, you have to do things asynchronously if they are not important for the users right now. We use Beanstalk because it's a good fit for us. Going back to MongoDB, it was going great until it wasn't. And you find that out in production when users are online and when it's difficult to fix those. So we had the replication issues. We had data type issues where 4-byte integer is not the same as an 8-byte integer, which you do not know until you see it in production and stuff like that. It was difficult to analyze data, which was a big minus for us because that's what we do. So we analyze data to show to the users. At that time, MongoDB had locking on a whole collection, and we do a lot of updates in a short amount of time, so the collection kept locking up. And there was no support for foreign keys, which was an issue because you want to have a database that has relations with other entities, and in our case, where we are really focused on an analytical thing, it wasn't really a great choice. So we started looking at the alternatives. And after researching, we figured out that the NoSQL wasn't really for us. It should be a relational database. And we came upon Postgres, and that's something we use today. And it's really awesome. And I'll tell you why. Because it's open source, it actually has great performance if you configure it correctly. You have to know how to do that, but it can have great performance. It has advanced SQL capabilities and minimal locking. It's called MVCC, multi-version concurrency control. Basically, you can read something, and that takes some time, and you can actually write at that same time to the data that you are reading. I'm not going to go into details, but it's awesome. And it's what enables us to have a lot of reads and a lot of writes at the same time without anything locking up. As far as numbers go, we have one machine that we tested can do 1 million queries per second and around 90,000 transactions per second. One transaction is actually 5 changing things. So you have 3 updates, 1 delete, and 1 insert. So that's a lot. Like, you can have 1 million selects and 500,000 updates. But the problem is we have users all around the world, so we cannot stop and do the migration from NoSQL to SQL. And in my mind, it looks something like this. So you're driving on a highway with 100 miles an hour, and you have to change the wheels. But since we were crazy and young and didn't see the issue in that, we said, you know what, screw it, we're gonna do it. And we actually did, and the process isn't actually that complicated. We wrote a tool to transfer the data from MongoDB to Postgres, and then just kept running that tool, which only moved the changes from the last run. So you just keep running it until the databases are synchronized, and then eventually you release it to the production. Again, it could be a long talk if I were to discuss how we actually did it, but it's possible. And as far as the results, so MongoDB has really simple replication. It has really simple configuration and leader election. In Postgres, you do not have that. It's much, much more difficult. So that's something we lost. But we gained stability, foreign keys, and analytical power. The moral of the story is sometimes you have to know that you made a mistake. With the technology, you cannot go straight into the wall. And sometimes it's best to change and try a different technology. When we did that, everything was more or less on autopilot. We had AWS, we had auto-scaling, everything worked. And I don't know if you can see, but here it's almost 17,000 people real time. Everything works, nothing breaks. And then you get to the interesting stuff. So we had an auto-scaling group, and it had Varnish on it and the backend servers. The problem with this is when you scale, when you auto-scale, each of the machines has its own local cache. And then all of the machines go to the backend, which means your cache is actually getting worse. And then if you extrapolate, the more machines you have, the less cache is effective. And then that basically means your auto-scaling doesn't really do much. So the way to solve it is to remove the Varnish from the auto-scaling group and just have it as a layer in front of the backend servers. And of course, you have to have 2 for redundancy. And this works really, really great. You can scale the layers separately. The problem with this, I mean, it's not a problem. I just find it irritating. You always have 2 requests to the backend because you have 2 machines. Wouldn't it be nice if it was just 1? Of course it would, because you can cut your cost in half. You need 50% less servers if, in average, you get 1 request. So the way to do it is to have a 2-layer architecture where you have the caching layer, and then all of those machines go to a single machine, which actually holds everything. And use that machine for memory to store the cache, and everything else to serve that cache to end users. The problem, of course, with this is a single point of failure. If this machine dies, everything dies. We were actually running this for quite some time in production. It worked great for us. Because, you know, fortune favors the stupid ones. But at a certain point in time, I said, okay, I have to be able to sleep without worrying if I'm going to be woken up because the machine is offline and then have to replace it. It was easier because we were in the cloud, so we could actually do that, but you want it to be on autopilot. So the way to solve this isn't actually all that difficult. You just, instead of having one machine, you have two or more machines, but for this simple example, I'm using two in each layer, where you just shard. So for a certain URL, it will always go to the same machine in the lower layer. And why two layers? Because you use this for bandwidth and for CPU, and if they do not have something in their cache, they will go to the second layer, and you use this to expand your caching capability. So we have like 6 nodes in the first and 3 nodes in the second, and it enables us to have almost the whole application is cached. So it allows you to have a really, really quick response. Varnish's response is like under 1 millisecond. So our average latency, our average response from the backend, even though we are using PHP, is around 3 milliseconds. So that's how long it takes for the response to be served to the user. And this is it. So what we can do with it, we can cache all of the things. And this is really important because we also took time to implement a purging library, an internal purging library that we actually open sourced. But the thing is, if you design your API to be cacheable, and you have a decent caching layer, and you know when something happens, when a change happens, when you know what you need to purge, you can get a system that's really, really, really fast, really scalable, robust, and is cheap, because having something in the cache is cheaper than recalculating it every time. So Amazon was working great, and we got to 54,000 users, and everything was working. And of course, when everything works, then you start having ideas. So what we could optimize, because we were in the cloud and megabytes are really expensive. If you do a lot of data, as we do, like traffic gets really expensive. We were at a point where our traffic was costing more than the compute resources. So we were spending more on traffic than we were spending on compute. And I did not like that. So I started looking what we could do to kind of offset that cost. And the thing about buying machines is if you go outside of the cloud, if you go to a dedicated machine, you do not have to buy it, you can rent it. The traffic is really, really cheap, even free in some cases. So what we wanted to do is move that caching layer, which is basically a separate layer that does not depend on anything. We wanted to move it outside of the cloud so we could get that free traffic. And we actually did this, and it was simple. You just move a couple of machines from Amazon to another provider, and we got a 10x reduction in the cost of traffic, which is a lot. And then it got us thinking. So this was really a great move to be able to kind of keep the cost of the service down. So what would happen if we were to migrate everything from cloud to the data center? And that, you have to keep in mind, at that point, cloud was all the rage. So we were, again, doing something that seemed stupid, because why would you move away from the cloud? The main thing is cost. So we figured that since we have the caching layer, it kind of absorbs the peaks. So your backend is always getting hit on the same. And we didn't actually have the need for autoscaler. And when we put everything to the paper, we then saw that we could actually have double the capacity just to be sure and just to be safe, and it would cost us a couple of times less. So we did that, and this is the graph of our infrastructure cost, and you can see that it actually went down a little bit. Now, this might seem impressive right now, because it's not a big difference until I overlay it with the number of users. So this is the number of users that we had on the platform, and this is the cost. So our users grew a couple of times more than it was at the beginning of the migration. So it makes a lot of sense for us to do this. This was in 2014, we hit the mark of 100,000 users real time. So that was interesting. And we have a really special relationship with our users, which is kind of a love-hate, because so when a match happens, we send out push notifications, right? So we want to send it as fast as possible so people can see that somebody scored a goal or that the match started or whatever. And what happens is a couple of million users get the same notification. They open up their mobile phone, they click the app. How does that look like? Like a DDoS attack on the servers. So we are basically doing a DDoS on ourselves. And we have Cloudflare, and Cloudflare has DDoS protection. You can guess where I'm going with this. So they started blocking our users because they thought they were bots. They weren't, they were just really fast in opening those notifications. So I had to go and talk with them to have a rule for us that is an exception which says do not trigger DDoS for this certain workload. So that was interesting things to solve. And then in 2017, we got to the mark of 230,000 users real time. The thing when you develop a certain product for a longer period of time, you get to have optimizations. You know, you can see how you can improve your system over time. So the best thing to use is application performance monitoring tool. You have a lot. This is a screenshot from New Relic, but you can use whatever you want. And it has a cool feature where it will not display the slowest thing, because the slowest thing is not the most important thing. Like if you have an endpoint that's only being hit once a day, you do not optimize that. But if you have an endpoint that's being hit on all the time and it's slow, then it makes sense to optimize that. And the way you do that is just multiply the number of requests with the average latency. You get the most, the slowest thing in your system. And when you go and see if you can optimize it, you can get this. So we reduce the latency by a factor of 4 or 5. Everybody has this in their system. You just need to know how to find it. And the way to find it is to have monitoring. If you do not have monitoring, you have to have it. Sometimes you cannot optimize, but you can increase the cache. That's why I said the cache was important. So this is the effect. When you increase the cache from 10 seconds to 1 minute, you get this much less actual requests on your server, which then drops the load on the server. So cache is really, really useful. In 2018, we had 310,000 real-time users, and everything was working with this system that was migrated off the cloud. But the question I get asked the most about the system that we have is, what happens if the number of users exceeds current capacity? Because you're not on the cloud, you cannot scale up, right? The way we do it is we have a dedicated machines, and then when a load gets high enough, we spin up virtual machines because our provider allows us to do that. And those virtual machines just join the cluster. The workload is then split among all of the machines and everything works. This happens rarely because the capacity is just right, but that's how we solve that potential issue. So it's kind of a hybrid cloud-ish thing. 2019 in September, it was 600,000 users, and we are waiting for that 1 million, but it took some time. And then like 1 or 2 months after that, it was 800,000. So those numbers really made us think, okay, we have something that's really, really cool on our hands. But the problem is physics. So our data center was in France, still is. And due to the way the world works, you have light, and light has a certain speed. And then when your users are far away from your central location, their experience is slow. So, and it's noticeable. So for users that are in Brazil, it's not the same as users for what users in Europe feel. And you can actually notice that. So we have a couple of power users. And I sent an email to one of those guys, and I said, can you please record the video of you using the application so I can see how it behaves? And he said, sure, no problem, like everything is working perfectly, the app is fast and whatnot. And I opened the video, and I saw this. So it was an empty screen with a loader. Honestly, I did not know we had a loader, because I'm from Europe. And in Europe, You have no loaders because it's instant. I said like around 3 milliseconds is the average response time, which is you just blink of an eye. So I said, okay, they are obviously having a worse experience that our European users have. They're just not aware because in Australia, like I guess everything is like that because they're so far away. So we got to thinking how we can solve this. The simplest way to solve it is just have your multiple data centers all around the world, but that's an issue. So you have to have databases, replications, multi-masters. It's horrible. But what we have is we have a caching layer, and that caching layer can be anywhere. So what we did was just, instead of having caching machines in just one location, we just put varnish all around the world. And what happens, and then you turn on geo-routing, so the users always go to the closest server. And what happened is in Australia, we got from half a second latency to, I think it's 40 milliseconds latency, which is almost imperceivable. So you go from half a second, which you can see, to something that you cannot see, and so they get kind of European experience over there as well. And what we saw after that was an increase in the users there because they can recognize that we are faster than the competition there, so they kind of start telling each other about that, and then your app grows. And finally, in 2020, we hit that 1 million mark, so it was a whole celebration in the company. And then I found out that data centers can burn. Fortunately, it wasn't our data center, but it got me thinking. So we were just in one data center. It was OVH. And I was like, okay, if this data center burned, then we would have an issue. And if you're in the cloud, it's simpler. You can just choose different AZs or configure the system. It works. But when you're on-prem, it's a bit more difficult. So what we ended up doing is we said, okay, we have to have 2 data centers. And we have to have the system where if one whole data center fails, we want it to kind of redistribute the load so it will work out of the box. And it's difficult to do if you're not on the cloud. You have to do a lot of stuff manually, which we didn't want to do. So what we ended up using is we said, okay, we are now ready to switch to Kubernetes. Before this, we were using Docker and Docker Swarm. Anybody knows what Docker Swarm is? Couple. Okay, quite a lot. Yeah, it's dead now. Kubernetes killed it. I would not recommend doing Kubernetes unless you know what you're doing. It's really hard. You do not know that it's hard until shit stops, right? We did this carefully. Why we chose Kubernetes is because it is data center aware. So that was something that was really important to us when we wanted to do multiple data centers. Kubernetes has a lot of tools that enable you to do that properly. For example, you can say, go to the database that is closest to you. So you do not have one worker going to a different data center just to fetch some data. You can have locality. The deployment is extremely easy. You just say, here's a new image, deploy. You have the same code on all of the machines. You can also have this in the cloud by using Amazon Machine Images or whatever. You can also run Docker. And upgrades. We just bump the base image and everything works. With that comes rollbacks. If you do something wrong and everything crashes or it's not working, you just roll back. It's a mechanism built in to the Kubernetes. So this is something that really enabled us to have cloud on our system, right? So we do not have the cloud, but we have all cloud-like capabilities that are useful for the system. In 2021, we got to 1.5 million users using this system. So running Kubernetes in 2 data centers and having a bunch of machines all over the world to help with the load. So we're using PHP as our backend, and the PHP has certain limitations. One of those is you cannot really do real-time updates. It's difficult. It's difficult to do real-time updates. So what our users actually do by using the application is they fetch data all the time, right? So every 10 seconds, you just pull the API, you see what the results are, you show it to the user. That's not really the most efficient thing to be using your resources. And also, it's kind of slow. So it's as fast as you pull the data, which like our users are really specific people. They really want everything right now, right away. So we said, okay, we have to have real-time updates. The way you do real-time updates is just have a persistent connection to a pub sub server where users, where applications actually subscribe to a topic, and then you just publish changes to that topic. So they get the changes instantly. And this is really hard to do. Like if you want to do it yourself, you have to have your machines configured to have the support for a lot of connections. So in our case, we have to have more than 2 million live connections. You have to know how to set up the machines for that. You also, if you're coding this software yourself, it's really tricky to keep all of that connection data and topics in memory. So just don't do it yourself. Like there's software that's written specifically for this. I did not know before we went into this what software we should be using, so we kind of experimented a bit, benchmarking, trying it out. The problem is you cannot really benchmark how things will behave in production, right? So the only way to know how it will behave in production is you just deploy it to 20 million users, you put something in production and you see if it works. Or you go to a talk and then somebody tells you what to use, right? So what we're using is this. It's Cloud Native Foundation project. It's called NATS. It doesn't stand for anything. It's just called NATS. And what it is it's simply a pub sub server. So the applications subscribe to a topic, and then you just publish things you want to it. We have it running on a couple of machines. It has support for cluster mode, which means it will auto balance and it will just work out of the box. And this is what enables us to have, and it's, of course, it's open source, it's cloud native. And this is what enables us to have millisecond dispatch to all of our users. So it takes around a couple of milliseconds to just deliver everything to all of the users all over the world. With regards to the actual speed of light, right? You cannot have faster than that. But it works. So what we have is PHP for the backend, and then all of the changes are published via NATS. And this works really, really great, because if this fails for whatever reason, the caching layer is so robust that people will always see some content. Like when we do database upgrades, you have to be offline if you do not fail over. People do not know that we are doing database upgrades. If we have issues with our database where we are offline, people do not know, because all of the main data is in the cache. So that's a really cool thing to have. And in front of everything is also Cloudflare, which also does a bit of caching. So in 2022, we were at 1.7 million, almost 1.8 of users real time. And this is the graph with our cost. So it has increased after some time. The main reason being is we started using Cloudflare we had the business package, which does help us with some stuff that's interesting. We also started doing machine learning. That's expensive. And we also moved to the second data center, and that's our current cost. I'm going to show later on how much it actually costs. So we also have a lot of data. We have 1 petabyte of data, and that has its own issues to solve. So if you're not on the cloud and you have 1 petabyte of data, it's really interesting to solve that. Because how can you store 1 petabyte? So before we started doing this, I did not know how to do that. So you kind of go around and start talking with people and seeing what kinds of different software can you use. If you're on the cloud, you just use Google BigQuery or whatever and just pay the price, which with this kind of data can get really expensive. So what we ended up doing is installing this. This is ClickHouse. It's a free tool from a company called Yandex. It is a beast. So it can. We have it storing 1 petabyte of data and scanning millions and millions of rows every second, and it works great. So if you have analytical workload and you want to do it yourself without paying for a cloud service, this is something you could use. They are actually using it as a backend for their service called Metrica, which is something like Google Analytics. So you can track users on the website. They're using this to power Metrica. And our current cost is just 1.8% of the revenue. So that's the main reason why we are doing all of these things, is because we want to keep the cost low. For this presentation, if you want to take something home, well, like the most important stuff is, I did not mention this explicitly, but it's important for scaling. You have to be stateless wherever possible, because that enables you to go to multiple machines. If you have state on one machine, you cannot scale efficiently. You have to know how your users interact with your application. That's really important, because then you can build your system so it's optimized for that usage. You cannot make a generic system and hope it will be fast and optimal. Cache. Seriously, like this, if you only remember one word, it's cache. It's so it enables you to have a system that's really fast, really robust, and really cheap. That's the most important thing. And also, you have to recognize the right tool for the job and change if necessary. If we didn't switch to Postgres, we wouldn't be able to scale to this level of users that we now have. And also, queue everything that is slow. That's a given. For any major application, for any serious system, you have to have everything fast, and everything that is slow has to be in a queue. And also, monitor everything, optimize something. You know, the saying, premature optimization is the root of all evil. That's true. So do not optimize unless you have the need for it. And to be able to optimize, you have to have monitoring. You have to know what your system is doing to be able to know how to fix it. Thank you. That's it. If you have any questions, now is the time. Yeah.
So how do you decide how long your caching will be?
That's a good question. So the question is, how do we decide how long the caching will be? So for our cache, for the match details, which can change second by second, it's 2 days. Which doesn't make sense, right? So what you do in that case is you purge the cache. So if you know that something changed, you have to know what resources you need to purge, and then you just purge them. The next request that will come will then be going to the backend and will be recached. But yeah, that's a difficult thing to do. You have to really think about how you have to know what resources you need to purge. For us, it's simpler because we wrote a tool that enables you to kind of annotate your endpoints, and you say this endpoint depends on this entity, and then when that entity changes, it will purge this endpoint. And internally, it builds out a graph of all of the URLs it needs to purge. It's open source. You can implement it in any language. You just need to take some time. Yeah.
You mentioned about Cloudflare. Were there some things that you cache at the CDN layer as well?
Yeah, so since the caching is happening at the HTTP layer, so whatever Varnish caches, also Cloudflare also caches. Cloudflare caches around 80% of everything, and then whatever goes to the Varnish is cached for another 95%. Total caching is around 99% for us. So it's a lot. That means that we only need 1% of the resources actually to serve all of this. But yeah, Cloudflare cache is a lot. Yeah.
How big is your cache?
How big is the cache? That's a good question. So I have to calculate. It's around 300 gigabytes of RAM. Not a lot.
One machine?
No. Spread over multiple machines. So we have dedicated machines and we are running PHP, so we have a lot of memory available. So we just spread out. It's free for us. So we just spread out varnishes in Kubernetes on every machine. It's a daemon set. So all of those have 16 gigs reserved for the varnish. We have 20 machines, which is around 300. Yeah. But you actually do not need a lot. So with just one machine with 16 gigabytes, you can get a really big impact on the system. And people usually think, well, my application is not really good for this because I cannot cache because it's user specific. We have a lot of user specific stuff in the application. You just have to organize your API to be able to use it. There are certain mechanisms. Again, a whole talk could be done about this. But if you just stay and think on how you can design your API, for example, things that change separately, you just put on different endpoints. You do not bundle it into one huge endpoint because then you have to purge it all the time. But if you have things that change every second and then you have things that change every day, you just put it on separate endpoints. But yeah.
Thank you. At the end, we saw that GCP appears for the data.
What?
At the end, we saw that GCP cloud appear in your cost of infrastructure.
Oh yeah, sorry, I did not. Yeah, so GCP is we export data from Firebase to Google BigQuery, but Google BigQuery is expensive, so we download it to ClickHouse. But again, you have to pay for the download and everything else, but we keep it in check. So we use GCP just to export data from Firebase and to be able to import it locally. Because that's the only way. You cannot export data from Firebase, the user data, without actually going to BigQuery. Yeah.
You said you need to monitor a lot of things and you seem to use a lot of cache. So you have key metric to monitor regarding the cache, its ratio, or
Yeah, we do. Because that's really important to us so we can track if we start doing something wrong, if the cache hit rate drops below a certain percentage, we get an alert so we can then check out and see what's going on. We have a lot of monitoring, and that's not something that was done in a day. So that's something we build out throughout the years. So when something breaks, I always say to my guys, like, it's acceptable to break stuff. But you always have to see what broke and why it broke, and then you have to know how to prevent it the next time, or at least be able to detect it early on. So every time we had an outage, we just created a monitoring for it, and then figure out what else could go wrong that's related to that, and then also put that in the monitoring. But yeah, as for the cache, we have a lot of different statistics. Varnish has a lot of statistics on their own, and you can just import it to Grafana or Prometheus or whatever. Yeah. Why did we use NATS? Oh, because it's a different use case. For Kafka, it's not really a great idea to have multiple consumers on the same topic. And also, it really wasn't built to be used by your end clients. So it's used more as an internal tool. This is built really for public-facing stuff. So you have clients that are really, you have clients for all of different platforms that are really written to be as small as possible. Kafka is not really oriented towards that. Yeah.
So we are only using ClickHouse for archiving.
Yeah. So not we actually do analytical workload on it, not just to archive stuff. So we have data going back 4 years for every user action, which is anonymized by Firebase. and then we aggregate that data, and then we do machine learning on that data, and all of the dashboards for sales and other departments are using that data from ClickHouse, and it can handle quite a lot. Yeah.
You said you had about one petabyte of data. Assume that is live data. Do you have any backup concepts for this data?
Yeah.
Because active, passive standby
Yeah.
doesn't really get it. If
Yeah.
some table is dropped and the drop is replicated, you're in deep shit.
Exactly. That's a good point. Yeah.
You tried it out.
Yeah.
1 petabyte takes.
Yeah, it's so to be honest, we do not restore it often, but we do dump the data from the ClickHouse, and then we upload it to Amazon Glacier Deep Storage, the cheapest one there is, which is expensive if you want to restore, but that's the last resort disaster recovery. But we do have everything dumped over there. But yeah, it's interesting thing to solve. ClickHouse also does really good compression. So the 1 petabyte of data isn't actually 1 petabyte on disk. It's less than that. And it also enables them to really read the data much faster from the disk. Okay, I'm here whole day and most of the day tomorrow. So if you wanna chat about anything, I'm here and I'm available. Okay, thank you.